Locomotives idle all night without running out of fuel for one simple reason. The tank is so enormous, and the idle burn so tiny by comparison, that a full night barely scratches the surface. A freight locomotive can sit rumbling in a yard for 10 or 12 hours, going absolutely nowhere, and still have well over 90% of its diesel left by morning. But that raises a stranger question. If the engine sips so little just sitting there, why not shut it off entirely and save every drop? The answer pulls you into a world of exhaust chemistry, frozen airlines, and a cost calculation railroads quietly settled decades ago. Start with the number that surprises everyone. A big diesel locomotive burns somewhere around 3 to 5 gallons of fuel an hour while idling. That sounds like a lot until you see the tank it's drawing from. A modern unit like an SD70AC carries roughly 4,900 gallons of diesel. An older workhorse holds well over 3,000. Compare that to your car, which tops out around 15 or 20 gallons, and the scale snaps into focus. A single locomotive hauls close to 200 times the fuel of a pickup truck. So when it idles overnight and burns maybe 40 to 60 gallons total, it's spending a rounding error. The tank looks barely touched at sunrise. The running out of fuel fear that feels so obvious from the outside simply isn't a real constraint. But that only deepens the mystery, because the reason the idle burn is so small is the same reason the engine is so big. These machines aren't sized for idling. They're sized for the brutal peak of dragging a mile-long train up a grade where the engine can gulp more than 200 gallons an hour at full throttle. At idle, almost none of that capacity is being used. The pistons turn lazily, the alternator spins at its lowest setting, the cooling fans cycle on and off, and the only real job left is keeping the support systems alive. So idling fuel isn't being spent to move freight at all. It's being spent to keep the locomotive awake. And if fuel were the only thing that mattered, you just shut it off. But it isn't, and here's where it gets interesting. It turns out that letting one of these engines idle for hours does almost no harm, while shutting it down and cooling it off can do a surprising amount. The problem starts with temperature. When a big diesel runs at very low load, its exhaust runs cool, too cool to fully burn the fuel being injected. The leftover fuel and oily soot collect in the exhaust system, a condition railroaders call wet stacking, and you can literally see it as dark residue building up around the stack and on the injector tips. The manufacturer's own manuals warn about it. Let the exhaust temperature sit too low for too long, and the deposits start to accumulate. The prescribed cure is to periodically run the engine hard, at high load, to push the temperature back up and burn the gunk away. And wet stacking is just the visible symptom. The deeper threat is what that unburned fuel does once it sneaks past the piston rings and mixes into the engine oil, a slow poisoning called oil dilution. As fuel contaminates the oil thins out and loses the additives that protect the engine. So bearings and cylinder liners begin to wear faster, and the odds of a serious failure climb. Operators take this seriously enough that they regularly pull oil samples and test them. A sudden spike in fuel contamination is a flashing red warning that something's wrong. Cool running causes trouble at the other end too, where water vapor condenses inside the engine and in cold weather turns into a mildly acidic sludge that quietly eats at metal surfaces in the crankcase and the turbocharger. That turbocharger deserves special attention because it's both critical and fragile. It depends on hot, clean exhaust to spin, and prolonged, cool idling lets soot and fuel cake onto its turbine blades. As those deposits build, the turbo loses efficiency, heat builds where it shouldn't, and the risk of cracking or outright failure rises. Field data has shown turbines exposed to long, cool, idle developing measurable carbon buildup in a matter of months. Put all of it together, wet stacking, fouled injectors, diluted oil, acidic condensation, a coking turbocharger, And you start to see why railroads don't treat shutting down as a free win. Cold starts and cool running carry their own bill, and it's paid in premature wear, more frequent overhauls, and expensive repairs. That's why even units that idle a lot get scheduled high-load runs and routine oil checks to keep them healthy. There's a second reason buried in the very design of these machines, and it catches almost everyone off guard. Modern freight locomotives are built around a single, massive engine doing all the work, rather than several smaller ones, and that wasn't an accident or mere tradition. One big engine meant a lower cost for every unit of power, fewer engines to buy, install, and overhaul, and decades of proof that a single well-built prime mover could survive the punishing demands of continuous duty year after year. It also simplified everything downstream. Fewer spare parts to stock, fewer systems for mechanics to learn, more locomotives kept in service. But that choice quietly locked in the operating logic that keeps these engines running even when they're sitting still, because one big engine doesn't have the flexibility to power down part of itself when the load is light. Railroads did test the alternative. There are genset locomotives that replace the single giant engine with 3 smaller ones, each able to start and stop on its own, so the machine burns only as much fuel as the moment demands. One engine idling, 2 or 3 firing up for heavier work. In yard switching, where the work is constant stop and go, these cut fuel use dramatically, sometimes by 1/3 to 1/2, and ran quieter too. But the experiment revealed a catch. 3 small engines meant 3 sets of filters, sensors, and control systems, more software to glitch, more specialized parts that weren't always on hand. In hard mainline service, the added complexity introduced new ways to fail. The lesson wasn't that the idea was bad, it was that every design is a balance, and fuel saved in one setting can be maintenance gained in another. Time and again, railroads chose the visible inefficiency of idling over the hidden uncertainties of something more complex, because simplicity and predictability usually win. The third reason has nothing to do with the engine itself and everything to do with the network it lives in, and it might be the most important of all. Every freight train depends on a continuous supply of compressed air in its brake line, and federal rules require that pressure stay above a set threshold. Shut a locomotive down and let it sit, and that air slowly leaks away through countless tiny gaps. When it's time to move, the crew can't just fire up and roll. They have to wait while the compressor recharges the entire brake line from end to end, a process that can stretch past 20 minutes on a long train. In a busy yard, or on a tight main line, that delay is simply unacceptable. The dependence runs deeper than brakes. Passenger trains and refrigerated freight rely on the locomotive for a steady stream of electricity, for heat, air conditioning, lighting, and keeping perishable cargo cold. Cut the engine, and all of that goes dark. Passengers lose climate control, safety systems trip, and a reefer car full of product starts warming toward spoilage. And the same logic extends to the people running the railroad. A locomotive that's idling is ready to move the instant a dispatcher calls. A locomotive that's shut down forces everyone to budget for restart time, air charging, and system checks. In a network where trains are scheduled to the minute, every one of those delays multiplies down the line. Layer on the regulatory picture, federal and state emissions rules that tighten the screws on pollution, but stop short of ordering blanket shutdowns, and you get a system that asks railroads to balance cleaner air against keeping the whole network fluid. So, how do they actually decide? They put 2 columns on a ledger. On one side is the cost of the fuel burned while idling, real money, but steady and predictable. A locomotive idling at 5 gallons an hour through a long night, at around $4 a gallon, burns a couple $100 before sunrise, and across a full year, a single unit's idle fuel bill can run into the tens of thousands. On the other side sits the cost of what happens when you shut engines down and cold start them too often. A turbocharger replacement running well into 5 figures, a full set of injectors costing thousands more, cylinder liner work on top of that, and at the extreme end, a complete prime mover overhaul that can reach into the hundreds of thousands of dollars. Every one of those repairs is triggered or accelerated by exactly the wear patterns that cool running and repeated cold starts create. When railroads ran that comparison decades ago, the answer was clear. For most units, the predictable cost of fuel beat the unpredictable cost and downtime of major repairs. Idling all night looks wasteful, but on the balance sheet it was often the cheaper of two expenses. That old math, though, is finally under real strain. Diesel prices that were once low and stable have swung hard, and when fuel gets expensive, a few $100s a night across thousands of locomotives becomes impossible to ignore. At the same time, the communities living next to rail yards have run out of patience with the constant low rumble and the haze of exhaust, and their complaints have pushed railroads toward real change, equipping switchers with cleaner systems, saving tens of thousands of gallons a year in single neighborhoods where residents demanded it. But the fleet itself changes slowly. Huge share of locomotives were built decades ago. New units trickle in only a handful at a time each year, and most of the older machines simply lack modern idle control electronics. So the legacy habit persists even as the pressure against it builds. The good news is that real solutions are arriving, just unevenly. The frontline tool is automatic engine start-stop, software that watches the locomotive's vital signs, the brake pressure, the temperatures, the battery charge, shuts the engine down when everything's safe, then restarts it the moment power is needed again. In yard pilots, it has cut nightly fuel use by double digits while keeping locomotives available for service, almost without exception. Battery hybrid locomotives push further, pairing a big battery with conventional diesels to soak up the idle moments and trim a train's total fuel use by over a tenth, though their cost keeps them on high-traffic corridors for now. And in fixed facilities, wayside electrification lets locomotives draw power from the grid and skip idling entirely, slashing yard fuel use, but only where the railroad can justify the steep installation cost. None of these replaces the legacy system overnight. Instead, railroads layer them in where each fits best, chasing incremental gains across a diverse, aging fleet. There's a human layer to all of this that's easy to miss. Every new system adds responsibility for the crews and mechanics, more diagnostics to learn, more sensors to watch, more that can go wrong mid-shift. Dispatchers and engineers are judged on delivering trains safely and on time, not on experimental fuel savings, so reliability is the currency they actually trade in. When the margin for error is measured in minutes, and a single failed start can strand equipment or cascade into missed schedules, a healthy caution toward unproven technology isn't stubbornness, it's hard-won experience. Can you really blame them? So tonight, while most machines sleep, hundreds of locomotives sit idling quietly in the dark, each burning just enough diesel to keep 4,000 horsepower ready on a moment's notice, and each with a tank so deep that the night barely registers. It isn't waste, and it isn't neglect. It's the product of brake rules written into federal law, the real risk of cold weather damage, and a cost calculation railroads made long ago and are only now beginning to revisit. The compromise keeps the freight moving, and the freight keeps the country moving with it. If you came here thinking an idling locomotive was just fuel poured down the drain and you're leaving with a sharper picture, that's exactly what this channel is for, the hidden engineering logic behind things you've walked past 100 times. Subscribe and stick around, because the next one will change how you see something else entirely.